All right, class, welcome to the continuation of 2.3 for the video, and particularly for Christopher. So just, and Kate's absent too, right? So just two. Okay, so let's go. Let's keep on going. We're going to enter into some trig stuff, which things we should be, let's see, it will be useful later on. How about that? We just want to prove it. We have already proved it graphically. We want to prove it now algebraically. That's what we want to do with the trig stuff. And then, yeah, that'll be good. And then we'll move on to continuity, which is 2.4. And then we have something called the rigorous approach of limits. So far, we've been looking at it graphically. We get some numbers there. But the question is, what's almost like the theoretical way of seeing it? That's the one we handle for 2.5. And it gets a little intense. So if you guys are ready for something intense, wait up for 2.5. All right, with that, let's go. Let's keep on going with this. I'm going to just, you guys have to help me out which example problem we're going to be on. We're good as we go. And what do I want to do? I'm going to do a pin. I'm going to do it this way today. Okay. We are on example 6, but before we get there, let's just do exercise 6. Let's do just a quick example. Maybe this will be interesting. Whenever you have a small number on top and a big number on the bottom, we tend to say it's going to go one way or another. It's going to go to the same number. We're good? I think you guys can realize that here. If we have a small number on top, like 1 over 10,000, yeah, that's going to go to 0. Pretty easy, right? And so I would say that limit is going to go to 0. Tell me if you guys agree or not. Okay, so then if we have, let's switch it around. So if we have, and really the issue is the zeros, right? And the issue is constants that are changing, constants that are moving away. So let me do this here. Let me do this here. Limit as x goes to infinity of 1 over x. Talk to me. What do you guys say? It goes to 0. Absolutely. Okay. That's what I kind of just want you guys to notice. That's one piece. The next piece is what happens if we go the other way. What happens is the limit as x goes to 0 of this. I'm sorry, x. I like this pen a lot better. Okay. Less chicken scratch. Okay, what do you guys say here? It's going to go to, so x becomes smaller, smaller, smaller. If you want to try it on your calculator, Enrique says it'll go to infinity. Agreed, disagreed, and try some numbers if you like. 1 over 0.1, 1 over 0.0001, 1 over 0.000001. Right, everybody okay there? Just want to make sure. If you need to try it on your calculator, try it. If you can kind of think about it like, oh yeah, absolutely, that's going to do that. Good there? Everybody agreed with Enrique? It's going to go to infinity. In fact, it's going to go to the positive infinity. We're good? So then we have the other issue. Remember, we have two different infinities. So then we have this. Then we have the limit as x goes to 0 of negative 1 over x. That's going to go to negative. Whoa, that infinity symbol is kind of funny. Negative infinity. Are we good there? Right, that little negative sign triggers a different way to go, right? It's going to go way, way down now. Okay, so then what happens here? Now let's go on to the exercise problem. We're good? Cool. And you guys tell me, stop me if you need to, okay? Otherwise, we'll just keep on jamming. This is 6, I believe. I need to know the limit as x goes to 2 from the left of this problem. Now we get to the fun stuff. All right, and talk to me as you do it. Talk to me if you need to. So we're approaching it from the left-hand side. Okay. And notice on the bottom, it is going to go to 0. If I plug in a 2, it's 0. Good there? Okay, so then the question becomes a few things here. In fact, let me do it this way here. Start looking at signs. This stays on top. Can I factor out the x on the bottom? Okay, there with the factoring. Bless you, I think. Okay. So then we're approaching 2 from the left-hand side. So we're looking at 1.9, right? 1.99, 1.999, 1.99999. And so as I do that, I think to myself, first of all, the bottom is going to go to 0. So these numbers are going to become super, super small. Okay, so then on the top does not go to 0. So then my question really is, am I going to go off to infinity or negative infinity? That's the only question at this point. And maybe, let's go for it here. So just kind of thinking intuitively here, 2 on top over here, if I were to plug in 2 on top, it would give me a negative on top. Everything good there? And if I plug in a 2 over here, that gets me a positive 2, right? I'm kind of approaching positive 2 there. I should do it this way here. And if you want to, the way the book does it, let me see the way the book does it for sure. It is in the form of this right here. So it's in this little form right here, F-O-R-M-E, form of k over 0. We're good? It's the k over 0 forms. The top is not going to 0. It's going to go to some kind of constant, but the bottom is. And so now the interest is just signs. We know it's going to go to infinity. We just need to know which one. And so with that, 2 plugged in would give me a negative here. A 2 plugged in here would be a positive here. And a 2 plugged in here would give me, and then this is where we got to think about it. If it's approaching from the left-hand side, positive or negative?
Negative.
It's a negative, I agree. So the total, grand total of this guy is that right there. Are we good? So let's go the other way. Sorry, let me mark this as A. Let me jump to this one as B. Switch it around just a bit. All yours for this one. And that one, and that one. And all right, let's see if this makes sense here. So limit as x approaches 2 from the positive side or the right side. And I'm going to factor it out. See things individually. And now we go with it here. So 2 going in there, 2 minus 3 is still a 1. That's still minus 1, so it would be a negative on top still. It's of the form k over 0, right? Everybody agree there? Jumping to the bottom here, that's going to be a positive for the 2. And then now we're approaching from 2.1, 2.01, 2.0001, 2.000001. Everybody okay with the plus sign this time? But then the whole thing goes down to a negative. So graphing, if I were to look at it graphically here, I know this right here. As x approaches 2 from the positive side, I don't know how this graph goes, but I know at least it's going to go this way. Okay? As it approaches from the left-hand side, I know it's going to go this way, and here's my asymptote if you want to see a graphical representation. That's what I just proved. Okay, are we good? Okay, one more thing to do. Exercise 7, and then we're going to get to the trig stuff here. Okay, one more other thing we've got to do is just this right here. So I'm going to give you a function. The function is that right there. X minus 5, square root of x minus 5, and I want to know this. I want to know the limit as x approaches 5, again, from the left-hand side of f of x. I want to know as it approaches from the right-hand side, and limit as it approaches 5 as the limit. Then I think we're all ready to go. All right, and this one, you do have to kind of have a sense of what the graph looks like, and at least domain. Remember domain with this stuff? So square root of x minus 5, the graph of it sort of looks like this, I believe. at x equals 1, 2, 3, 4, 5. There's my graph, and it just kind of spins off this direction. Graph it if you need to. So then the question is, what's the limit as x approaches 5 from the left-hand side? Any guesses? All right, no guesses. Okay, I'm going to write 3 letters down then. Good. It's no number at all, right? Because there's the domain doesn't even go to the left-hand side, right? The function itself starts right at 5. So there is no graph at all. There's that. Okay, so then let's go from the right-hand side. Right-hand side, even the graph sort of shows you what should be there, right? And so as you go from the right-hand side, it's going down, down, down until it hits 0 and it stops at 0. Oh, question is, can we plug in a 0? Right, that's one of our methods, right? If I can plug in a 0 to my function, that's going to be my limit. As long as I know that it's bending towards that way, right? It's not just the one single dot out in space, right? We saw that with the piecewise functions, right? You can go different directions. You can put a little dot somewhere wherever you like, which is not really the piece there. Okay, are we good? You guys have some strange looks on your faces, so I just want to know, is it just Monday, or is it just kind of like, yeah, what's up? What limits? What? Slow process? Are we okay? Am I okay with 0 here?
Yeah.
Because as it approaches, it's going to go down to 0 here. Okay, so the C, the answer is? Does not exist, yeah. Because remember, the last one is just a computation. Last one is just a computation of the previous 2. Previous 2 are the same, the last one is the same. If they're different, then it's not. Okay. True in a...
Actually, you can't use, there's lots of other things that we don't do right now.
No, the way we define it, it does not exist. Yeah, just because there's no domain. Okay, so now the fun part. You guys ready? Da, 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 da. We have the squeeze theorem.
What?
There is a theorem. It's called the squeeze theorem. So now the question is, so let's kind of go back in our minds here of limits. So if you plug it in, you're good to go, right? As long as you know it's a continuous function. Sometimes we have to manipulate stuff, right? Sometimes we have to put the fractions together. We did that last time, right? Sometimes we separate fractions themselves. We get complex fractions, we simplify. And sometimes it just wonderfully works out. Well, sometimes, especially with trig functions, that stuff does not work out. So then we got to figure out other ways and other means to do it here. So what does the squeeze theorem imply? And so what does it mean? Yes, absolutely, between 2 pieces. So if I have this, I'm going to define them loosely here. If f of x is less than a g of x is less than an h of x. If I have 3 functions, and I get my g function to be in the middle between the 2. Then, so if this, and we've got another condition here, the limit as x approaches a, let's just say, right, of f of x is equal to the limit as x approaches a of h of x, which is actually L, then, da, 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 what do we know? We've squeezed g of x in between those. That means g of x has to have an L. It's the same limit. So graphically, if you want to see a graph of it, it's almost like doing this. And so here is, let's say this is f of x right here. Here's going to be g of x. And what's another? Ooh, let's see. That's kind of the way we write it usually, and h of x. And as long as g of x and h of x go down and they're hit one single value, you know g of x has to be that value as well. Okay, does the graph help? And so then this would be like A, and that would be your limit right there, right? Because everybody combined together here. Okay, so how does this help us? Let's go with it here. What exercise problem are we on? Perfect. Fine. Limit as x goes to 0. And let's do an easy one just to sort of see how it works. Okay, no.
Sorry, Mr. Manager, does that say x cos?
Limit as x goes to 0 of x times cosine of x.
Okay, thanks.
Good.
Just 0.
It's a 0. You can plug it in right then and there, right? How do I want to show it? Why do I want to do it? Let's see. And so at one point you could do that here. One second. Let me give you one little minute here.
That Christopher is fast forwarding through this right now.
Lost my train of thought here. We could just plug it in, because that's just the plug-in value, right? X goes in there, and no matter what cosine of x is going to be, the product of those two is just 0, right? What we are trying to do is trying to just do this here. Let's do it by squeeze theorem. Again, same exact concept. Let's just do it this way here. So tell me, agree or disagree, if I take cosine of x, isn't cosine of x, the highest it could go is 1, lowest it can go is -1? I think I remember that, yep. Okay, so how about this here? How about if we introduce x all the way across here? And so we multiply everything through by x. Will that work? I think so. So, everybody okay with this? Not okay with that. It should be like this. We're good there? Okay.
Where is the x into the cosine of x? Yeah.
Oh, you did write that.
Good, good. Okay, so again, just a quick example here. This one, I think we've set it up well. Here's my f of x right here. Here's my g of x in the middle, and my h of x at the end. Are we good? In fact, we can even write it like this. Tell me if you guys agree here. We can even write it, because this is a negative x, that's a positive x. Isn't this also true? Oh, sorry, just looking at something here. Absolute value of x, is that right? You have something that looks like that as well? Would that be true? You guys talk to me here. Or it's the absolute value of this right here. Agree there? And this is the formula for the and relationship for absolute value. And so we have the limit as x goes to 0 of x itself, that's 0. The 0 is already there. Then this little piece goes there too. Not sure if we want that included in there.
Why is the negative x turn into 0? Why isn't it just turn to x? You get the absolute value of.
Sorry, I was going somewhere here. Don't need to go there because we can get our limits right over here from on top. So tell me if true. So limit as x goes to 0 of negative x. 0. As x goes to 0 of x itself, then therefore, then the limit as x goes to 0 of x times cosine of x is also 0. Are we good?
Yeah.
So as long as we can find something that our function is greater than and less than, then we can, if we can get the limits of those, then it's the same. And if they're the same.
If they're the same, that means the middle one has to also be there.
Okay.
Cool.
Are we going to do that theorem?
The squeeze theorem, will actually prove the theorem itself? No, we're just going to use it. I think we're ready here. I think we're ready for this one. Exercise 8. So these two that we have to prove from previous. Let's try to prove this one here off to the side. Prove that the limit as theta goes to 0, sine theta over theta. Okay, real quick here in our notes back to 2.2. Did we prove this already? You guys know what this one equals to? You guys can thumb back to your notes.
So we did sine 1 over x. We talked about sine 1 over x. Oh wait, no, yeah, we did example 7b is what I have.
Yes,
Sine x over x.
We did it by table and graph, both. I think we did it by both.
We definitely did it by graph. I think, yeah.
It kind of went like this, didn't it? Like that?
Yes.
Yeah.
Wait, well, no, it was,
We did it.
yeah.
We did it though,
I
right?
have it down as that limit.
Sounds
Yeah.
as 1. Okay, so let's go with it here. So the question is, how do we prove this? There's the fun part. We'll need this for later on as well. We'll see it later on. So let's jam. Huh. Okay, see if that works out or not. Let's go with it here. So tell me if you guys agree or disagree. 0 is less than theta is less than pi over 2. So we have to kind of think about one little thing here. And here's our little trick. Whoa, that's a step.
Why did we
So here it is.
Sine theta, or sine 0 would be 0. And
Yeah, that.
0.
Sure. We'll go with it here. So first things first is we're going to prove it from the right-hand side. We prove it from the right-hand side, we can prove it from the left-hand side. So first thing that we're going to do is we're going to lock our theta between 0 and 2 pi, pi over 2, right? Because we're going to be in quadrant 1. And so...
Oh, is aren't all... What did you say about our limits always... not the same.
Okay. Once this is in place, once we lock this in place, let's take a look at this little graph here. Let's see if this makes sense. It's going to be unit circle. Here's my unit circle. And let's say I have a little point here, right? Because I already declared I'm in quadrant 1, right? Perfect. So let's see if this makes sense. In fact, let's do this here. Let's make sure that this guy is a 1, right? We're on the unit circle. And let's see what happens here. I'm going to drop this down. And I'm going to have, tell me if you guys agree or disagree. This guy's theta, isn't it not?
Yeah.
Right, it's the radian measurement of theta, right, coming down. And then if I do this, which is pretty cool there, I'm going to say this is tangent. Tell me if you guys agree. That little distance of that to that is tangent. Whoa, tell me if you guys ever seen that before. Have you seen that before? Did you guys ever see it?
Yeah, it looks familiar, but I don't remember how.
Yeah.
It's tangent.
There's one graphic that has all the 6 trig functions. It's just this one, it looks kind of weird at first, but it's like, there's it is. It's all the graphical representation of all the different trig functions. And so this little line here, from here to here, that represents tangent, because at 45 degrees, notice this here piece and that piece are going to be exactly the same. Good? And it's a ratio. So as you bring this down, tangent gets smaller and smaller and smaller, and eventually goes to 0. Good there. So that little distance from here to here, that represents tangent. Where's sine theta?
That's the triangle.
It's the center triangle right there. Good there, because sine theta is the opposite side over hypotenuse, which is still 1. Therefore, it's just the opposite side. Good. That is so cool. So I think I've got it. I've got it squeezed in. But sine theta is right here. I want sine theta to be in the middle, don't I? So again, this is not like, you guys should know this, right? This is, we've done it before. Oh, wow, that's awesome. Let me show you guys so we can use it later on. We're good? That's kind of what this is. So let's do this here. Since we want sine theta in the middle, let's divide everything by sine theta. So let's take this guy. Let's divide by sine theta. Let's see what we get.
Oh, wait, is that?
Talk to me.
No, I'm going.
This is one of those in mathematics where someone noticed it, like, oh, wow, that is awesome, right? And it opened up a whole new branch of mathematics, right? So we're following in those person's footsteps as we open this up.
Yeah, I'm definitely not happy with it.
Okay,
Can I ask?
good.
I'm not quite getting how we know that tangent is that other.
Gotcha, okay, yeah. We noticed that tangent is opposite over adjacent, right? Let's see. Let me see if I can do that here. Let's see. At a 45 degree, it almost works out that if you look at this side here, right, and you start measuring this side out each time, right, it will give you the ratio of sine over cosine. And I think the way we just look at it, a whole bunch of different tables. And we do it on
It's just like, you don't even
geo board.
see that it always works.
No, I think you should be able to, I don't know, let me look up the proof for it. Because graphically it works out. I know in geometry, I used to teach geometry, we would do that. We'd have this little board up, it's a geo board, and I would move the line like, oh, look, tangent and this one are exactly the same all the time.
Yeah.
That's so cool. So that means that must be tangent. So we do it that way. Okay, good. But I'll look up the little proof for it. So this should be, okay, are we set here? So sine has to be in the middle. Let me add some more. Some more slides here. Okay. Let's do this here. Sine theta, sine theta, sine theta. And you guys tell me, what do we have here? Ooh, remember those identities we learned from trig class, right? Tangent over sine? I don't know. Cosine, everybody agree there? Cosine, okay.
You can flip those if you want to run it the other way.
There we go. Let's flip them around. So whenever we take a reciprocal of an inequality, right? And if it's set up, you guys talk to me if you guys agree. We flip it around. This one, real quick here. Let's take a look at this. This is sine over cosine, right? Over sine itself. Is that right? So that means this would be sine theta over cosine theta multiplied by 1 over sine theta. Oh, hold on. So this one, we almost got stuck. This is 1 over cosine, agreed?
Yeah.
Okay, so the flip of it would be cosine itself. Agreed there.
Wow, that's fun. That's cool.
Okay, so then we can move it around. Let's move this around. I like to see it like this, right? Cosine theta is less than sine theta over theta is less than 1. Are we good? Oh yeah, I think we've got it. So let's see if this makes sense. Limit as theta goes to 0, what's cosine theta going to be? 1, right? Everybody agreed? It's we looked at it earlier, right? Cosine limit is 1. Limit as theta goes to 0 of 1 itself. Sorry guys, I'm doing my chicken scratch again. Everybody agreed with 1? Did we squeeze it?
Yeah.
Limit as theta goes to 0 of sine theta over theta is equal to 1. Just proved it. We're awesome. So we proved it. Good.
Do we use this to prove limits then?
It's a method, right? The squeeze theorem, you mean?
Yeah.
Squeeze theorem is a method normally to prove trig functions here. Yeah, just because we a lot easier for that.
Graphically, is it not proving it? Or is this somehow more authoritative than
Looking at a graph,
Yeah.
looking at a graph is very, very soft. We consider it mathematics.
Yeah, it's a method
Right.
because
If
you
you
can
can-
draw it or your computer draw it. Because sometimes, I don't know.
And then math is built upon deductions and proofs.
Yeah.
So if you don't set up a proof, you technically haven't proved it. You look at some numbers,
Yeah.
right? So you look at it graphically like, hey, that might be true. Let me see if I can prove it. Then when we look at it algebraically, we solve it. But really, actually, we haven't proved it. Are we good? We haven't proved a single limit yet. And we're not going to prove it until 2.5. We're just looking at them algebraically. Okay, you guys get next. Here's the other one that's important one. This is exercise 9, I believe.
I think it's
10, awesome, thank you. We're in double digits. Okay, prove for me this. So of course we might need some help. Okay, did we see this one before?
Yeah.
And real quick here, let's see. Anybody flip back to their notes here? What did we get for a limit for this initially? So I should say prove, huh? Prove.
0.
Oh, this one became 0. Okay.
I mean, this data in the box, that makes sense. Picking up data in the box. Although, never mind.
Cool. So the squeeze theorem we use to prove sine theta over theta, right? Once we have that established, we know that is a result. So whenever that's going to happen, we know it's going to be a 1. We can use that in a whole bunch of different formulas now. Right? We'll need it for later on. So how do I want to get sine theta out of this thing. So let me start here. What are we in time-wise here? Yep, I got multiply by Enrique. What should we multiply by?
I was thinking like, wait, 1 minus cosine theta is like 1 minus cosine squared theta. But,
Perfect. How do we get there? You're in the right direction. Absolutely. I'm gonna go with that. The conjugate. You guys remember the conjugates from algebra? Oh man, look at this. There we go. I think I like that. So on top, I'm thinking I'm looking at theta goes to 0 of, and you guys have to do it yourself here. Tell me if you guys agree that that's going to be 1 minus cosine squared theta. Okay, in the bottom I do have a theta, and then I also have a 1 plus cosine theta. Awesome. We're getting somewhere.
The top of sine squared.
Sine squared theta. Let's go with that. That. Okay, can I pull out my little, my new little formula? I think I can I?
You also could do, well, you can split it off with the denominator and the top too, so you can get sine theta.
Perfect, yeah, I want that guy, uh-huh.
You would have like 1 times sine theta over 20 cosine theta.
That works by me, absolutely works by me. That's cool, okay, so then I know, oh, so hold on, my question is this, can I plug in the 0 now into 1 plus cosine theta?
Yeah.
That would be 2, okay, sounds good. Right, because my problem initially was I can't make this a 0, right? Because it gets me undefined term and I'm in trouble.
Right, but if you plug in 0 to sine theta,
It's a 0 on the top too.
so it doesn't have to become 0.
It's not on the top.
Yeah, no, I'm not saying from the fine, but doesn't that second fraction just become
We want it to be 0 because that's.
right? Yeah, I get that, but
Yeah, we can plug it as 0. As long as the 0 is on top, you're fine. You just can't have 0 at the bottom. So we got
it goes to the second fraction goes to the number 2 or something.
On the bottom.
At the bottom, yeah.
Uh-huh.
Yeah, sorry. Because
So
1
that's
plus cosine theta would be 2.
Yeah.
Sine theta.
I didn't realize it was
Done.
at the bottom.
okay, done. We've proved it, guys. We've proved the 2 that are super, super duper important to prove for calculus as we see these. We'll see these 2 formulas later on. Okay. I'm so glad. Just like that. See this here. Interesting. Okay. And then let's go with one. This is 11. All yours from beginning to end, just so we got it. 11. Prove. All right, so first things first is check to see, actually not prove, sorry, I should say find, right? Because we don't, not in proofs yet here. Find this. All right, will look something like the last one for some reason. Let's just do that. Something similar to it, yeah. We're going to multiply by. 1 plus cosine theta on the bottom. Yeah. Awesome. I think we have something looks like I guess we could show the limit, right? If one thing is the same with the one thing on top, that means this guy has to be a 1. Could just cancel themselves out, or you could just cancel them off. That's no problem. And same thing, is that right? So we got 0 here in our hands. Okay, cool. Okay, we are done with 2.3. We're going to look at continuity in 2.4. I think hopefully we can do it one day here. Hopefully we can classify the different continuities here. My question is, do you guys have any homework questions as of right now?
I didn't bring my book.
Gotcha, okay.
I didn't do the homework yet because I was studying.
Gotcha, okay, for the test here. So I have an extra book in case you want to. If you guys want to start the next 15 minutes or so, just start doing the homework. That's fine. Come by, help you guys. I can, let's see, I guess I can broadcast it as well. So let me do this. Let me end. So this would be end of lecture for 2.3.